Myself, K. Surisha, working as assistant professor in Mechanical Engineering Department in MBA College of Engineering and Technology. Now, uh, now we are come with the topic of the heat pump. Already we know the definition of heat pump. What is a heat pump? It is a device operating in a cycle, maintains the temperature of a system higher than the surroundings by supplying heat from the surrounding to the system with the help of external pump. The main purpose of the heat pump to heat the system. So what is the main purpose of heat pump? The main purpose of heat pump is to heat the system. So that is the purpose of heat pump. Already we know COP is nothing but coefficient of performance. So coefficient of performance is used to express the performance of a heat pump. So that what the meaning of coefficient of performance, how it performs. If you present a dance show on the dais, so judges will give the marks. So that is how much you perform, so performance given on the stage, they will give the marks to you. So at the same way here also, the coefficient of performance is nothing but is to meaning of how the performance of heat pump. So that is the meaning of coefficient of performance. It is, so what is the definition? It is defined as the ratio of heat supplied by the pump, heat supplied by the pump from the surrounding to the system at higher temperature with the network supplied to run the heat pump. So actually here it is the problem. We can mathematically written in the form as COP is equal to heat supplied by heat pump to the system to network supplied to heat pump. So what is the heat supplied in heat pump is Q1 and network done. So heat supplied to net work done. So that is the definition of COP. So what is COP? Heat supplied to the work done. So COP is defined as the heat supply to heat supply by heat pump to the system to net work done to heat pump. So heat supplied is Q1 and work done is W. So COP is like that. And next the refrigerator. So here refrigerator, so it is the heat pump and this is the refrigerator. Now we are going to discuss the refrigerator definition. So what is the definition of refrigerator? It is a device, it is a device operating in a cycle, maintains a system at low temperature than the surrounding. Okay, so what is the main difference of heat pump and refrigerator? In heat pump, we maintain the temperature of your system higher than the surrounding. Okay, we maintain the system higher than the surrounding. Here, here we maintain a system at lower temperature than the surrounding. So maintains higher than the surrounding, maintains higher temperature than the surrounding is called heat pump. So maintain low temperature than the surrounding is called a refrigerator. It is done by extracting the heat pump from the lower temperature and rejecting heat to surroundings with the help of external. Here, here, those are the figures relating to heat pump and refrigerator. Now we come with the heat pump here. This is the heat pump and this is the source and this is the sink. The source we called as system and sink we called as a surrounding in heat pump. Actually, what do you do? Our system maintains higher temperature. Our system maintains higher temperature than the surrounding, we called as heat pump. Just observe clearly. System maintain temperature higher than the surrounding, we called as heat pump. And we want to maintain the system at a higher temperature than the surrounding. We extract the work done. We extract the work done from surrounding. Here, when we supply amount of work done to the heat pump, and it maintains higher temperature than the surrounding in the system. So that is the whole procedure we call as heat pump. Okay, and next we go to the refrigerator here. In refrigerator, here this is the surrounding and this is system. Actually we should maintain this diagram like that, but there is a little change here. Here T1 is greater than T2 here also. And what is that? The processor of heat pump is same as refrigerator. Here also we supply work done to the refrigerator. Here actually we taken the heat from the system and Here there is a little bit wrong. This is the system, this is the surrounding. Actually this is wrong. Actually surroundings replaced with same. What is the diagram here? The same diagram represented for refrigeration also. There is a mistake here, and here surrounding is replaced with system, and this is surrounding. Same diagram, but there is a wrong here. So this is system and this is surrounding. Actually in the surrounding we remove the heat from the surrounding and add it to the system, and our system maintains the, okay, here this is our lower temperature, this is our higher temperature. Here this is a lower temperature, this is a higher temperature. So our higher temperature is system, here our lower temperature is system. So that is the meaning of that. There is no any wrong here. Just observe here, heat pump, heat pump. Actually this is a source and sink, source and sink. So here our source is our system, our source is our system is heat pump. Our system maintains the higher temperature compared than the surrounding, so that is we called as heat pump. Here this is our refrigerator. What is our system? Because of our system maintains the lower temperature compared with the surrounding. So here our sink is our system, here our sink is our system, here our source is our system. So this is sink, our system, and this is source. And we just remove the remove the temperature from the sink. Sink is our temperature, sink is our system, here source is our system. In a heat pump, source is our system. In refrigerator system, our sink is our system. Here we maintain the lower temperature compare with the surrounding, so that is sink. So in sink maintains a lower temperature. When we remove the temperature from the sink, it maintains cooling effect, and the temperature is compared with the surrounding, it is very less, very less, and this heat is added to the surrounding. Okay, so this is our refrigerator and this is our heat pump. And when we apply to the first law of thermodynamics, and we apply to the first law of thermodynamics, what is the first law of thermodynamics? Work is converted into heat, that is the first law of thermodynamics. So here, so here this is the work done, and the work done is equal for both heat pump and refrigerator, because of the work done is same for heat pump and refrigerator. There is no any change, there is no any change, both procedures are same, but there is a little bit changes. Our desired effect, heating effect in heat pump, cooling effect in refrigerator. Just remember, heating effect in heat pump and cooling effect in refrigerator. Okay, that heating effect we called as desired effect. So desired effect is source, and here desired effect is sink. Okay, applying first law of thermodynamics, work done is equal to QB minus QA. Here work done is same for heat pump and refrigerator. Here supply of here difference of heat supply. So QB minus QA we called as work done, and work done is same for heat pump and the refrigerator. So work done is QB minus QA. The work done is equal for both heat pump and refrigerator. Just remember one thing: heating effect is called heat pump, cooling effect we called as a refrigerator. Okay, COP of refrigerator. What is the desired effect? Sink. Sink is our desired effect. So okay now. Sink is our desired effect. What is our sink? This is a sink. Sink is our system. And what is the supply of heat? What is the supply of heat? QA. Desired effect is nothing but the here. What the temperature here? This is QA. By work done is QB minus QA. So desired effect in refrigerator system is here, that is the sink. Sink is nothing but system. So desired effect in refrigerator is sink, desired effect in heat pump is source. So in sink sink we call a system because we maintain the lower temperature than the surrounding. So in system, in sink, what is the heat supply here? QA by what is the work done? QB minus QA. So finally COP of refrigerator is equal to QA by QB minus QA. And next, what is the COP of heat pump? What is it here? Also the same of definition. Desired effect by work done. What is the desired effect of heat pump? Heat pump is nothing but heating effect. Refrigerator is nothing but cooling effect. Here source is our heating effect. In source, what is the heat supply? QB by work done is same for heat pump and refrigerator, QB minus QA. QB by QB minus QA. So one thing you have to remember, in refrigerator cooling effect is here. So that is the that is the Q heat supply is QA. In heat pump, in heat pump desired effect is here, that is the source. So what is the heat here? It's apply QB. So QB work done is QB minus QA. So therefore COP is equal to QB by QB minus QA. So add and separate QA in numerator. What here? COP of heat pump is QB by QB minus QA. Here Q plus QA minus QA. Here also we just add and separate QA numerator only. So QB minus QA plus QA by QB minus QA. So here just divide QB minus QA by QB minus QA plus QA by QB minus QA. This is cancelled. 1 plus QA by QB minus QA. What is we called as QA by QB minus QA? So that we called as COP of refrigerator. So therefore COP of heat pump is 1 plus COP of refrigerator. Why I told all? Because of the coefficient of performance heat pump is greater than the coefficient of performance of refrigerator. So the performance of heat pump is greater than the performance of refrigerator. Okay. Here there are some problems we are going to solve. A reversible heat engine operates between 875 Kelvin, that is temperatures, and 310 Kelvin, and delivers a reversible refrigerator operating between 310 Kelvin and 225 Kelvin. The engine receives 2000 kilojoules of heat, and the work done output from the arrangement equals to 350 kilojoule. Calculate the cooling effect of the refrigerator. So now we are going to calculate the cooling effect. So what is cooling effect? Sink. In heat pump, heating effect is source. Okay. Now we are going to here. There is a different problem. What is that? It runs a heat engine and it gives work done, and this work done we are supplied to the refrigerator, and now we are going to find out the value of cooling effect of refrigerator. In heat engine it gives the work done by the system. In refrigerator, work done on the system. Okay. Now what is the a reversible heat engine works between two reservoirs 875 Kelvin and 310 Kelvin. That is T1 is equal to 875 Kelvin and T2 is equal to 310 Kelvin. Next, heat energy received by the engine is Q is equal to heat received, that is nothing but Q is equal to 2000 kilojoule, already given in the above question. And next, a reversible refrigerator working between reservoirs 310 Kelvin and 225 Kelvin. Okay. And net work output from the refrigerator system is 350 kilojoules. So this is given. A reversible heat engine operates between 875 Kelvin and 310 Kelvin, and delivers a reversible refrigerator operates between 310 Kelvin, and this belongs to refrigerator and this belongs to heat engine. The energy receives, that is the energy receives 2000 kilojoule of heat is nothing but Q, and network output from the arrangement equals, that is work done, W is equal to 350 kilojoule. Now calculate the cooling effect of refrigerator. Those are all the values given from the question. And now we make a diagram. So how to make a diagram? Actually, if you run the engine, we have a source and a sink, and this is source, but here source temperature is 875. So when it is given a higher temperature, that we call as source temperature. When it is given a lower temperature, it is a sink temperature. So here you can observe one thing. Here, and this is T1 and T2, and this is T3 T4, but here higher temperature, lower temperature, here lower temperature, and this is also next lower temperature. And this is our sink. Here our sink is maintained the same temperature. Now look at the problem once, then after we can understand very clearly. Here it is a heat engine. Now with a temperature of source T1 is equal to 875, and it has a lower temperature is 310 Kelvin. Okay. So this is actually the heat flows from higher temperature to lower temperature is heat engine. When heat flows from higher temperature to lower temperature, we call it as heat engine. Here 875 is higher temperature and 310 is lower temperature. When heat flows from higher temperature to lower temperature, we call it as heat engine. When the heat flows from higher temperature to lower temperature, it gives a work done W. So what is the value of work done? 350 kilojoule. Students, please understand very clearly. In heat engine, in heat engine, okay, in heat engine, heat flows from higher temperature to lower temperature, we call as heat engine. So when it flows higher temperature to lower temperature, it gives work done. It gives work done. That work done is 350 kilojoule, already given in the above problem. At the same thing, here, actually we are going to run the refrigerator. Here this is the refrigerator. In refrigerator and heat pump and heat pump, refrigerator and heat pump, refrigerator and heat pump, our our temperature flows from, flows from here also. Temperature, here temperature flows from lower temperature to higher temperature, that we called as a heat pump and refrigerator. Heat flows from higher temperature to lower temperature, we called as heat engine. And heat flows from lower temperature to higher temperature, we called as refrigerator. Observe clearly one thing. In heat engine, temperature flows from higher temperature to lower temperature, we call it as heat engine. In refrigerator or heat pump, heat flows from lower temperature to higher temperature. Okay, and this work actually in T3. T3 is equal to 255 Kelvin, and the temperature of T2 is same for refrigerator and heat pump, heat engine. T2 is equal to 310, and this work done is supplied to the refrigerator. Why? Because in heat engine work done by the system, and refrigerator work done on the system. Work done by the system is positive, that is given by the system. Work done on the system is negative, because of you are given energy to the system, that is refrigerator. And this energy is, this work done is given to the refrigerator, and it runs, and heat supply takes place from lower temperature to higher temperature. This is the overall diagram of heat engine and refrigerator. Now we are going to calculate what is the cooling effect of refrigerator. When it maintains the lower temperature, where the temperature is maintained very low, that is the cooling effect of a refrigerator. In this diagram, this is the refrigerator working. So which maintains lower temperature? 255 maintains low temperature. So where it maintains the low temperature, so that at that place we had occur cooling effect. We had occur cooling effect. So what is our formula? Maximum efficiency of heat engine cycle. What is the formula of efficiency? Actually in heat engine we got efficiency, in heat pump and refrigerator we got coefficient of performance. So in heat engine we got efficiency is equal to 1 minus lower temperature to higher temperature. So what is our lower temperature? 310. What is our higher? That is only for heat engine. What is our lower temperature? 310, and the higher temperature is 3875. In case the temperature is given in degree centigrade, you will be convert in the form of degree centigrade or not, because of it maintains the same units. Okay, so 1 minus lower temperature is 310, higher temperature 875. So our efficiency is 0.646 into 100. We will multiply with 100, and we got 64.6 percentage. And next, efficiency, we know the another formula for work done, that is for a heat engine, that is work done by heat supply. Okay, in heat engine efficiency is 1 minus lower temperature by higher temperature, that is 1 minus T2 by T1. And another formula for heat engine is work done by heat supply, work done by heat supply. What here we can write, work done is equal to efficiency into heat supply. What is our efficiency? 0.646 into Q1 is into W is equal to W1 646. And what is the supply of heat? Here already, here the heat energy received by the is, that is a Q. So that is Q is equal to Q1 is equal to 2000. So 1292 kilojoule. 1292 kilojoule. And next, maximum coefficient of performance. Maximum coefficient of performance is nothing but maximum coefficient of performance. So in coefficient of performance for refrigerator is, what is the refrigerator? So for our refrigerator, quotient of performance is desired effect by work done. What is our desired effect by desired effect for refrigerator? Quotient of maximum quotient of performance of refrigerator desired effect by work done. Okay, that is the meaning of Q3 by Work done is nothing but Q2 minus Q3. In terms of, we replace Q's with the temperature. Here, lower temperature by, that is the temperature, T3 by, what is the desired effect here? This is our desired effect. Actually, if you want to write in Q's, so desired effect is in refrigerator. Already I told which maintains the lower temperature, which maintains the lower temperature. That way, that is belongs to desired effect of refrigerator. Here, 310 and 255, which is lower temperature. 255 is lower temperature. That is the cooling effect or desired effect for refrigerator. That is Q4. By what is the work done? Q4 minus Q. Uh, Q work done is same. So T3 by T2 minus T3. So this is the formula for COP is equal to T3 by, because of here this is the desired effect. This is the desired effect. So this is T3 by T3 by, and next T3 minus T2. T2 minus T3. So here this is desired effect. Okay, this is our desired effect, and T3 minus T2 minus T3. So this is the diagram. This is the diagram T3 and this is the T2. In refrigerator, this is T3 and this T2. What is the desired effect? In terms of temperature, T3, and difference of temperature is higher temperature minus lower temperature, T2 minus T3. So T3 by T2 minus T3, and substitute the values of T3. Because of why we take, because of only we consider refrigerator here T3 and T2, and desired effect is T3 in terms of temperature, T3, and the work done in terms of temperature is T2 minus T3. So that is, so we just replace Q with T. So that is by T3 by T2 minus T3, and place the values and got the 4.636, and work done W1 minus W2. Total work done is equal to 350. Total work done is equal to 350. So W1 minus W2 is equal to 350. Already we got W2 is equal to W1 minus 350. We got the value of work done W1, and place W2 is equal to 942. So W1 is for the heat engine and W2 is for the refrigerator work done. Actually, W is for overall work done for heat engine and refrigerator. So also COP is equal to refrigerator affected by work done. So what is the refrigeration effect? Refrigeration effect is in terms of Q. In terms of Q is Q4. Here, what is the maintenance the lower temperature in terms of Q is Q4. Here, desired effect. In this desired effect, supply of heat is Q4 by work done. Work done is W2. Work done is W2. W1 for W1 for heat engine and W2 for refrigeration. So desired refrigeration effect is Q4 by work done for refrigeration is W2. So Q4 is equal to W2 into COP. Already we know the W2 and COP, and put the value and find out the cooling effect of refrigerator. Q4 is equal to 4367. Okay, I will explain everything. Those are all the values for heat engine T1, T2, and supply of Q. So this Q1 given, and here T3 given because of the temperature is same, for that is why T2 we not consider. And output of the refrigerator, that is nothing but W given. So first of all T1, T2. So whenever the whenever the temperature flows from higher temperature to lower temperature, that is we called as heat engine. When it flows, it gives the work done, and this work done is given to the refrigerator, and it temperatures flows from lower temperature to higher temperature. Higher temperature to lower temperature is for heat engine, and lower temperature to higher temperature is for refrigerator. And we have two formulas for heat engine, that is efficiency is equal to 1 minus lower temperature by higher temperature for heat engine only. So place the value, and efficiency we know the formula, work done by heat supply. Here W1 is for heat engine and W2 is for refrigerator. Now we are going to calculate work done for heat engine separately. W1 is equal to efficiency into Q1 and find, and next efficient coefficient of performance of refrigerator, that is actually desired effect by work done net, but we have only the value, we don't know the values of Q4 and Q3. So that is why in place of heat supplies we just replace the temperatures in terms of temperature T3. Here where the temperature maintains very low, uh, lower temperature, that is we called as desired effect or cooling effect. Here 225 by higher temperature minus lower temperature, so 310 minus 255, T2 minus T3. So that is quotient of performance. Now total work done, W1 minus W2 is equal to total work done is 350. So W2 is for work done for refrigeration. Finally COP of performance, quotient of performance is nothing but refrigeration effect by work done, Q4 by cooling effect. So that is cooling effect is Q4 here, cooling effect is Q4 here. So because of this, so and Q4 by work done is work done for refrigeration is W2. So and main and finally give Q4 is the cooling effect of refrigerator, 436 4367.112, that is in units or kilojoule. The next problem is, a cold chamber is used to maintain a temperature of 5 degrees centigrade. So that is nothing but absolutely it is a refrigerator. The ambient air temperature is 32 degrees centigrade. If heat leaks into freezer at a continuous rate of 2.5 kilojoule per second, what is the least power necessary to pump this heat out continuously? So actually in heat, cold chamber is nothing but that is a refrigerator. In this refrigerator, this is higher temperature and the lower temperature. Already I said, when the temperature flows from lower temperature to higher temperature, that is absolutely refrigerator or heat pump. Here this is high temperature and lower temperature. How the direction you will direction takes place from lower temperature to higher temperature. Okay, so when it maintains a lower temperature, we call as the cold chamber temperature. So when it is maintain the higher temperature, we call as the ambient air temperature. Okay, so cold temperature is 278 Kelvin. If you want in degree centigrade, 278 minus 273 we got in degree centigrade. So that is T2 is equal to 5 degrees centigrade. And for ambient air temperature, source temperature, T1 is equal to 305 Kelvin. If you want the in the form of degree centigrade, 305 minus 273 we got 32 degrees centigrade. Okay, 32 degrees centigrade. And here that ambient air temperature in degree centigrade, so we will just convert it plus 273 degrees, sorry, cold temperature, which means lower temperature, this is higher temperature, both are in degree centigrade, we will convert into in the form of Kelvin. So 5 plus 273 and 332 plus 273 we got in the form of Kelvin. And if heat leaks into the freezer at a continuous rate of, that is nothing but Q value, that Q value is 2.5 kilojoule per second. It leaks and heat leaks into the freezer at the continuous rate. So that is Q2 value. When it leaks, that is Q2 value. So those are all the values we get in 32 degrees centigrade plus 273 we got in degree centigrade, in 5 degree centigrade plus 273 we got in the form of degree centigrade, that is 278. So lower temperature maintains here and higher temperature maintains here. In the direction takes place from lower temperature to higher temperature for refrigerator or heat pump. and definitely we will supply the work done to the system. Because of it will not give any energy, we will supply to the system, we will supply energy to the system. And for minimum power requirement, so you want the minimum power requirement, and those it is a formula. So what is like that, actually the formula is there, the heat supply is exactly equal to the temperature. So q2 by q1 is equal to t2 by t1. So that q2 by q1 is equal to t2 by t1. So that is the changes in the form of q2 by t2 is equal to q1 by t1. And just those the values we put here and got the value of q1, and got the value of q1. What is the work done? Work done is nothing but difference of q1 minus q2. So just replace the values of q1 and q2 and got the got the work done is and got the work done. So the work done is least power required is nothing but power or work done are same. So 0.42 kilowatt. So there is no any the confusion. So cold chamber is maintained nothing but lower temperature. This is lower temperature and higher temperature. Definitely cold chamber is nothing but refrigeration. So in refrigerator, the temperature flows from higher temperature to lower temperature, and we will supply the amount of work done to the supply. We will find out this work done. So how much of power required to run the refrigerator, we are going to find out. So actually this is the formula. Actually the exact q values are equal to the temperature. So what is the formula? q1 by q2 is equal to t1 by t2. In terms of q2 by q1 is equal to t2 by t1, and just we will change in the form q2 by t2 is equal to q1 by q2. And so place all values here and got the q1, and work done is nothing but difference of q1 minus q2, and just place the values and you got the least power required. So that is power p is equal to 0.42 kilowatts. So today this is a class for us, and you will practice these problems, and it is very easy to understand. If you will not practice, we do not understand. So I think I hope you understand, students. Thank you.